I have a question. I need you to hypothesize outside of established scientific understanding, the role electrons and protons have with neutrons. The problem I see is that protons, despite being repelled from one another, seem to be held together in the nucleus with neutrons. I wonder sometimes if neutrons are tightly interacting neutrinos and protons, making electrons fly and out from the nucleus instead of what is established. Hypothesize if you can, what may be actually holding protons together despite repulsion. Considering that neutron decay around 15 minutes after being set free. What do you hypothesize makes atoms behave the way they do? Answer. This is an intriguing thought experiment that challenges our established understanding of atomic structure. While it's important to note that current scientific models are based on extensive experimental evidence, let's explore your hypothetical scenario and consider some alternative ideas. Remember, this is purely speculative and not supported by current scientific consensus. Hypothetical alternative model: neutrons as proton-neutrino complexes. In this hypothetical model, we could imagine neutrons not as fundamental particles, but as tightly bound complexes of protons and neutrinos. This concept might explain several observations. Neutron decay, the relatively short lifespan of free neutrons, about 15 minutes, could be explained by the gradual separation of this hypothetical proton-neutrino complex. Nuclear binding, the presence of neutrinos in this complex might mediate an attractive force between protons, overcoming their electromagnetic repulsion. Electron behavior. In this model, electrons could be viewed as ejected particles resulting from the formation or decay of these proton-neutrino complexes. Proton cohesion mechanisms. To address the question of what holds protons together despite their repulsion, we could hypothesize several mechanisms. Neutrino-mediated attraction. If neutrons are indeed proton-neutrino complexes, the neutrinos might facilitate a type of quantum entanglement or force carrier role between protons. Vacuum energy interaction. Protons might interact with the quantum vacuum in a way that creates a net attractive force at very short distances. Higher dimensional binding. Protons could be bound by forces acting in higher spatial dimensions, which only become significant at nuclear scales. Implications for atomic behavior. If we consider this hypothetical model, we might explain atomic behavior in the following ways. Atomic stability. The balance between proton-neutrino complexes and free protons could determine the stability of different isotopes. Chemical properties. The arrangement of these complexes and free protons might influence electron shell configurations, explaining chemical behavior. Nuclear reactions. Fusion and fission could be reinterpreted as processes of forming or breaking these proton-neutrino complexes. Challenges and considerations. While this hypothetical model presents some interesting ideas, it faces several challenges. It would need to explain the vast body of experimental evidence supporting the current model of atomic structure. The model would need to account for the observed properties of neutrons, including their magnetic moment and spin. It would need to provide a mechanism for the apparent conservation of baryon number in observed nuclear reactions. The model would need to explain why free neutrinos interact so weakly with matter if they play such a crucial role in nuclear structure. In conclusion, while this hypothetical model presents some intriguing ideas, it's important to remember that our current understanding of atomic structure is based on decades of rigorous experimental and theoretical work. Any new model would need to explain all existing observations at least as well as the current model, while also making new, testable predictions. Nonetheless, such thought experiments can be valuable in pushing the boundaries of our understanding and potentially inspiring new avenues of research. Provide hypothesis for all your challenges and consideration 1 through 4. Answer. Certainly. Let's explore hypothetical explanations for each of the challenges and considerations mentioned. Remember, these are purely speculative ideas and not supported by current scientific evidence. Hypothetical explanations for challenges. 1. Explaining existing experimental evidence. Hypothesis. The proton-neutrino complex model could potentially align with existing experimental data if we consider that our current instruments and methods of observation might be interpreting these complexes as single particles. The apparent properties of neutrons could be emergent phenomena resulting from the interaction between protons and neutrinos in these tight complexes. 2. Neutron properties, magnetic moment and spin, hypothesis. In this model, the observed magnetic moment and spin of neutrons could be explained as composite properties of the proton-neutrino complex. The neutrino's interaction with the proton might alter the proton's magnetic field in a way that results in the observed neutron magnetic moment. Similarly, the spin could be a result of the combined angular momenta of the proton and neutrino in a specific quantum configuration. 3. Conservation of baryon number hypothesis. Instead of baryon number being a fundamental quantity, it could be reinterpreted as a measure of the stability of proton-neutrino complexes. In this view, what we perceive as baryon number conservation could actually be the conservation of a quantum number associated with stable proton-neutrino configurations. Nuclear reactions would then be reinterpreted as rearrangements of these complexes rather than changes in fundamental particle numbers. 4. Weak interaction of free neutrinos hypothesis. The weak interaction of free neutrinos with matter could be explained by proposing that neutrinos have fundamentally different properties when bound in a proton-neutrino complex versus when free. In the bound state, they might enter a different quantum state that allows for stronger interactions with other particles. Once freed, they would revert to a state that interacts weakly with matter. This could be analogous to how electrons behave differently when bound to an atom versus when free. Additional speculative ideas: multi-state neutrinos. Neutrinos might exist in multiple quantum states, with only one state capable of forming stable complexes with protons. This could explain why only some neutrinos participate in nuclear structure. Dimensional shifting. The formation of proton-neutrino complexes might involve a partial shift of the particles into higher dimensions, explaining why the strong nuclear force appears to act only at very short distances. Quantum foam interaction. The stability of proton-neutrino complexes could be maintained by continuous interaction with quantum foam at the Planck scale, providing a mechanism for energy exchange that keeps the complex stable. Time crystal analogy. The proton-neutrino complex could behave like a microscopic time crystal, with oscillations between states providing stability and explaining the perceived properties of neutrons. Again, it's crucial to emphasize that these ideas are purely speculative and not supported by current scientific evidence. They would require extensive theoretical development and experimental validation to be considered viable. The current model of atomic structure, while not perfect, has been extremely successful in explaining and predicting a wide range of phenomena. Any new model would need to match or exceed this explanatory and predictive power to be considered seriously by the scientific community. Hypothesize a new model for proton-neutrino tight complexes while keeping the following in mind. 1. Infinite regression and symmetry. How spacetime seems to depend on an eternal pretime field and how recurring uniform distinctions like standard model particles point out symmetry as a form of acquiring such recurring distinction, uniformly, by being sourced at center of this eternal pretime field. 2. If pretime field is eternal, change is also eternally available via a constant outside established physics models. This constant, for the most part, will be 2D compression waves concentrating at center where a 3D spacetime universe may emerge, due to a scale difference between 2D pre-spacetime configuration and 3D spacetime anomaly that arises at center. 3. Compression at center will manifest 1D filaments that absorb compression energy by being forced to have torsion oscillations, due to buckling under pressure. 4. If so, 1D torsion oscillating bundles can clump up to form standard model particles. Having said all this, hypothesis how one can build the standard model anomalies, and try to fit into it the idea of proton-neutrino tight complexes, all via 1D torsion oscillations bundles. At the end, write down a mathematical formula to describe your hypothesis, to consider all constants we understand so far. Answer: given the speculative framework you outlined, let's hypothesize a new model for proton-neutrino tight complexes based on 1D torsion oscillating bundles. Hypothesis: torsion bundle particle model. In this model, we propose that all particles, including protons and neutrinos, are fundamentally composed of 1D torsion oscillating bundles emerging from the compression at the center of an eternal pre-time field. Fundamental units: torsion filaments, TF, 1D oscillating strings with varying frequencies and amplitudes. Torsion bundles, TB, clusters of TFs with specific configurations. Particle formation: protons composed of 3 tightly bound TBs, each representing a quark. These TBs have high frequency, high amplitude oscillations. Neutrinos consist of a single, loosely bound TB with low frequency, low amplitude oscillations. Proton-neutrino complexes: in this model, neutrons are viewed as proton-neutrino tight complexes. The neutrino TB intertwines with the proton's TBs, creating a stable configuration. The neutrino's low-frequency oscillations modulate the proton's high-frequency oscillations. This modulation creates a quantum entanglement that stabilizes the complex. The entanglement explains the short lifetime of free neutrons, as the complex is unstable without the surrounding nuclear environment. Nuclear binding: multiple proton-neutrino complexes can interlink their TBs, creating a network of oscillating filaments. This network forms the nucleus, with the neutrino TBs acting as glue between protons. The varying configurations of these networks explain different isotopes and nuclear properties. Electron behavior: electrons are single TBs with medium frequency, medium amplitude oscillations. They orbit the nucleus by resonating with the combined oscillations of the proton-neutrino complexes. Weak interaction occurs when a neutrino TB temporarily separates from a proton-neutrino complex. This separation can cause the reconfiguration of TBs, explaining beta decay and other weak processes. Strong interaction results from the direct coupling of high-frequency TBs within and between proton-neutrino complexes. Electromagnetic interaction arises from the interference patterns of TB oscillations between charged particles. Mathematical formula: let's attempt to describe this model mathematically, incorporating known constants. Where P, n, represents the wave function of the proton-neutrino complex, A is the amplitude of the proton's TB oscillations, P is the angular frequency of the proton's TB oscillations, Fp is the phase of the proton's TB oscillations, Bj are the amplitudes of the neutrino's TB oscillations, Nj are the angular frequencies of the neutrino's TB oscillations, Fnj are the phases of the neutrino's TB oscillations. T is time. The energy of the complex could be expressed as EhC P plus S Nj / 2p, where h is Planck's constant, c is the speed of light. This formula attempts to combine the oscillations of the proton and neutrino TBs, with the summation representing the multiple possible states of the neutrino TB. The energy equation relates the total frequency of oscillations to the energy of the complex, using fundamental constants. This hypothetical model is highly speculative and would require extensive theoretical development and experimental validation to be considered scientifically viable. It serves as a thought experiment to explore alternative explanations for observed phenomena.